So I will continue with my presentation about lattice results. Yesterday, basically, I mean, the outline was up to here. So this is the point where we arrived yesterday with the results regarding the topological susceptibility at 0 temperature. Now, today we will consider determinations going beyond the quadratic behavior of the free energy as a function of theta. So we will go to the quartic corrections, meaning determinations of the B2 coefficients. We will illustrate the difficulties, numerical difficulties which are involved. And that will be an occasion also to discuss more deeply the large-Nscaling of theta dependence. Then I will show you how the theta dependence changes as we cross the confinement, deconfinement transition in pure gauge theories. And then we will go to results regarding full QCD. So QCD with dynamical quarks, where there is in some sense more fun because it is phenomenologically more relevant, but there are also more problems, as we will see, both from an algorithmic point of view and also from the point of view of the approach to the continuum limit. So let me go to the last slide of yesterday's lecture, which was the following. I mean, showing the behavior of the topological susceptibility as a function of 1 over n squared. I mean, so these are results for 3 colors, 4 colors, and 6 colors. And the result is that indeed the topological susceptibility approaches, in pure gauge, approaches a finite value, which is in agreement with the Veneziano mechanism to explain the large mass of the eta prime meson. So in some sense, this is already in agreement with the large-Nscaling proposed by Witten. Anyway, the large-Nscaling proposed by Witten, this large-N Witten ansatz, tells us more than that. I mean, the question is whether the theta dependence follows a behavior which is proportional to a cosine of theta, which is the prediction of the dilute Instanton gas approximation, or instead we have a behavior where if we parameterize the dependence of the vacuum energy as follows, as a quadratic term plus corrections, if the scaling, the Witten ansatz is true, I mean that the true scaling variable is theta over n, and I remember you that this ansatz basically derives from the requirement that the theta dependence is non-trivial even in the large n limit, and from the observation that the variable which enters the Lagrangian at non-zero theta is actually theta over n. I mean, if you adopt the scaling with the Toft coupling in the large n limit. So according to this ansatz, the prediction is that these corrections to the purely quadratic dependence scale as inverse powers of the number of colors as follows. So B2 must be of order 1 over nc squared and so on. So in some sense, since a finite value of the topological susceptibility is not compatible with the dilute Instanton gas approximation, because in that case we would expect a vanishing topological susceptibility. So we expect that this other possibility is the one which is realized. But if we don't have any results of these further coefficients, we actually cannot say. So here we meet a problem, a numerical problem, and the problem is that the determination of these coefficients from simulations at theta equals 0 is quite challenging. Why? Well, basically, I remember you that these coefficients measure how the theta dependence deviates from a purely quadratic dependence, which is the one that you expect if the topological charge is distributed according to a Gaussian distribution. So these coefficients measure deviations from a purely Gaussian distribution in the topological charge distribution. Now, what happens in a few words, I mean, this is quite heuristic, but it is actually what happens, is that when you go to the large volume limit, since different regions of space-time are decorrelated from each other, in any case, the distribution of the topological charge approaches a Gaussian, just because of the central limit theorem. I mean, you are, in some sense, summing distributions over different portions of space-time. So, your task, I mean, to detect the value of these B2N coefficients is to measure these small deviations from a Gaussian from a distribution which is approaching a Gaussian in the large volume limit. Okay, so the task is more and more difficult as you approach the thermodynamical limit in your lattice. You can look at the problem in another way. Since the topological susceptibility is finite, and the expectation value of Q square is the topological susceptibility multiplied by the 4 volume, that means that the fluctuations of the topological charge have a variance or a standard deviation which is proportional to the square root of the 4 volume. Okay, so you have fluctuations of topological charge proportional to the square root of the 4 volume. On the other hand, when you define these coefficients B2N, you can prove, I mean, we checked that last week, that these B2N coefficients are related, are proportional times some finite factor, are proportional to the ratios of the cumulants of the topological charge distribution. Okay, now these cumulants are combinations of expectation values of the of some powers of Q. For instance, the B2 itself is the first one is minus 1 over 12 times Q to the 4th minus 3 times Q squared again, and then divided by Q squared. So the numerator of this appearing here in these coefficients comes out from the subtraction of, in this case 2, but when you go to higher order, of several expectation values. And each of these expectation values are of the order, at the numerator, of Q to the 2n plus 2. I mean, in the case of B2, since the fluctuations are proportional to the square root of the volume, the fluctuations of the terms entering the numerator here are fluctuating like the volume to the power 2. Okay, n plus 1, where n is the coefficients entering here. Okay, so that when finally, when you divide by the fluctuations expected also in the denominator, and when you consider that the finally, since it has to be a finite number, at the end, after the subtractions, the order of magnitude of the numerator has to be the same order of magnitude of the denominator, okay, because this is a finite ratio after all. I mean, they scale overall like the volume, both the numerator and the denominator, but the numerator comes from a subtraction of averages which scale like an higher power of the volume. So finally, you can deduce that the expected noise to signal ratio for these coefficients scales like the 4 volume to the power of n. So for instance, for B2, it is expected to scale proportionally to the 4 volume of your lattice. And this is the noise to signal ratio. So that means that the signal to noise ratio will become very soon poor, as you increase the volume. Okay, and the last point is what I explained before. I mean that after all, this is what we expect by the central limit theorem. So you need to go to very large statistics in order to obtain a careful determination of these coefficients, but the large statistics can become prohibitive as you reach a large volume. On the other hand, you need to go to a large volume. I mean, if you try to determine these B2 coefficients, for instance, from a small volume, you are sure that that will produce a fake signal. I mean, let me explain why. Suppose that your, let me do it here. So suppose that the volume is so small that that Q square, which is the topological susceptibility times the 4 volume, suppose that this quantity is much less than 1. Okay, so that your volume is very small. That means that since the expectation value of Q square is much less than 1, that means that if I call P of Q the probability distribution of the topological charge, that means that the probability distribution of, let me say, plus minus 1 is much smaller than the probability of the zero topological sector. Okay, because at the end you have the expectation value of Q square is much less than 1. Okay, so and so on. I mean, as you increase the value of Q, the absolute value of Q, the probability is less and less, because that means that the probability of finding a non-zero topological charge in your small 4 volume is very small. That means that when you write down the partition function z of theta, which can be written as the sum over Q of this probability distribution times e to the I theta Q, then you can just take into consideration the first non-trivial topological sectors. I mean, if you have that P plus minus 1 is much less than P0 and higher values are even more suppressed, then in this sum you can just take some finite value, which is P0 plus 2 times P of 1 times cos theta, and this is proportional to 1 plus 2 pi 1 over pi 0 times cos theta. Okay, so basically you obtain in this approximation, you end up with a Dilute-Nielsen gas approximation. I mean, if you take the logarithm of this, then the logarithm which will be proportional to the cosine of theta. So that means that you have you end up with Diga. So if your volume is too small, you will see a fake Diga signal anyway. Okay, even if on a large volume the Dilute-Nielsen gas approximation is not working. Basically, because on the small volume the topological charge distribution is just non-zero, just for Q equals 0 or plus minus 1, and then you don't see anything else apart from that. Okay, and this is compatible with Diga. So you need to go to a large volume, and you need to face with this problem as you go to a large volume where the fluctuations are too large. Now, a possible way out of this is the following: is to add, at least to improve this signal to noise ratio, is to add a direct theta term in your simulation. As we discussed last week, I mean, if you add a non-zero theta term, then the path integral measure becomes complex, so you have a sign problem. But in any case, you can play the game of using an imaginary theta term in the action, which makes the simulation, the distribution positive definite again. And then you can perform analytic continuation. I mean, what I mean, if you make a Taylor expansion of the free energy density as a function of theta, and then you're supposed to analytically continue from theta. You set theta equal to I times theta I, which is the imaginary part of theta. Then you can easily check that the dependence that you had before turns into this dependence as a function of this theta I. Okay, you just get a minus sign in front, alternating minus sign because of the imaginary I. Okay, then you can take the derivative of this free energy density, and then you obtain the expectation value of q squared, q to the cube, and so on. If you just take derivatives of this free energy density, carry information about these coefficients chi, b2, b4. But the improvement is that now even the expectation value of q, which at theta equals 0 is 0, even the expectation value of q has the information, if you determine the behavior of this expectation value as a function of theta I, has information not only about the topological susceptibility, but also about b2, b4, and so on. Now, since this quantity is much less noisy than the higher order cumulants, that means that by adding a source term to the action, you are able to obtain information from a less noisy quantity on the quantities that you are interested in. Okay, so basically this is the rationale at the basis of this method of the imaginary theta. Now, if you want to put this strategy on the lattice, then you need to add an exponential minus theta L times QL in the path integral weight. Now the point is, what is the choice for this topological charge QL? I mean, we discussed that there are several possible choices, but now you have to face the one problem, that this definition of topological charge enters directly in your simulation. So it's not just an observable now, but you have to take care of it in your Monte Carlo simulation. So you would like to have the simplest possible definition. Otherwise, it will be a nightmare to make the numerical, to adapt the algorithm and include this weight in the simulation. And the most elementary definition is the standard gluonic definition with no cooling, no smoothing, okay, which I discussed yesterday. Let me go a few slides before. Okay, this was the simplest gluonic definition. Actually, this is not the simplest one. This is already symmetrized, but on all the directions. But from the point of view of the structure of the operator, it is the simplest because it is just the, I write again the picture. It is just the combination of two plaquettes. Okay, that means that this is linear in the links variable. Okay, because each of these operator contains one link just one time. So this is linear in the link variables. And that means that if you adopt this definition of topological charge and you add this term to the action, then you have just to modify a standard hit-bath algorithm. I mean, you can still use a hit-bath algorithm, and just you have to change the definition of the force, I mean, of the sum of the staples to include also this operator. But it's not really a nightmare, just that you have to write down the code, but you can use the same code, okay? So it is more convenient. But of course, if you use make use of this operator in the action, you have to take into account that the gluonic, the standard gluonic discretization renormalizes multiplicatively. So QL is Z time has a multiplicative normalization constant in front of the relation with the standard topological of the true topological background, and that means that this renormalization of the topological charge turns into a renormalization of the theta parameter that you add in the action, so that finally you have this relation between the parameter that you really add to the action and the imaginary theta that that you have. Okay, so the previous relations that I wrote here, okay, had to be modified as follows. I mean, you have to add the proper powers of this normalization constant in front of theta L every time theta L appears in these expressions. Okay, then you can measure these quantities, and this is an example. I mean, you have here the expectation values at the same time of q squared, q to the cube, and q to the fourth, the connected expectation values divided by the Ford volume. And what you can see here is a sort of global fit where you fit these dependencies at the same time. And since you see that the same parameters appear in all the different expectation values, from a global fit, you can determine in a quite robust way all these quantities, including the renormalization constant, which comes out as a bonus of the method. And finally, you can determine quite precisely also, apart from the susceptibility, also B2 and maybe also the further ones. Do you have any questions on the method? Okay, let me go on. So let me go to the results. I mean, in this picture, in the first picture on the top, you can see the determinations of this coefficient B2 as it evolved during the years. I mean, so the first determination was in 2002 from Levio, Panagopoulos, and Vicari. Then there was a determination of mine. This was obtained actually by the field theoretic method, I mean, by subtractions over normalizations, which in this case is quite involved, but you can do it also in this old way of computing the additive normalizations for the fourth order term and subtract them. And as you can see, all these determinations were quite noisy. I mean, if you look at the scale, the error bars were all of the order of 20 going up to 50%, okay, relative error. Okay, and then finally, there is this determination, which is the most precise one, and where you have an error which is at the level of a few percent, and this was obtained with this method of the imaginary theta source, okay, which gives to this, brings to this improvement. And now, this improvement is actually what you need if you want to check the large-Nscaling of this coefficient, because I mean, if you already have an error of 50% with SU3, how can you check that B2 is scaling like 1 over n squared as you go to larger n? I mean, if you have such large errors, it is not feasible to check that it is scaling like 1 over n squared. If the error is at the order of percent, then you can try to check this, and this is what has been done in this later paper, where the same technique of the adding an imaginary theta term has been applied also to n equal 4 and 6. And you can see the determinations of B2 in these cases. B2 comes out to be negative. And you can see that this is a fit with a 1 over n squared behavior, which reproduces the behavior of the data quite well. So for sure, we can see that B2 is going to 0 as n goes to infinity, and it is in agreement with the 1 over n squared behavior. So it is in agreement with the large n scaling predicted by Edward Witten in the 80s. Do you have questions? Okay, fine.
Sorry, one thing, maybe the slide before this. Okay, so here you have, okay. So you determine the 3 parameters, B2, I mean, you can determine up to 3 parameters with 4 simultaneous fits. With the 4 cumulants, you have B2, B4, and Z. That's how you determine Z.
Yeah, exactly. Of course, you can you can also determine it independently. I mean, the Z can be also determined independently, and it is consistent with the determination that you get from the fit. Okay.
Okay.
So I mean, there is much more to be said about this fit, because of course the series here is infinite. I mean, you can add as much term as you want. So as you, of course, you use a truncate version of the series, so you are introducing some systematics. Okay. So for instance, you have to check that including or not including the B4 contribution does not lead to modifications of the determinations in the other parameters. So you have to check that the systematics of the truncation of the Taylor series expansion does not influence the determination of previous parameters. All these checks, of course, have been done in the actual determination. And then another observation is that, of course, that the fourth order cumulant brings poor information to the global fit. So even if you discard it, you can see here that the data have very large errors. And so much of the information comes from the first 2 or 3. Okay. Now, an important point is to comment on this value that we obtained for the coefficients in front of 1 over n squared. Why? Because and when people think to this large scaling predicted by Witten, let me go to this large scaling predicted by Witten, where the scaling variable is theta over n, compared to what is predicted by the Duluth-Hinselton gas approximation, where the variable is just theta appearing in the cosine. Now, sometimes people have a picture where in the Duluth-Hinselton gas approximation, the topological structures are instantons carrying integer topological charge. While in this regime where the large scaling works, the relevant degrees of freedom are some fluctuations of the gauge field, which have a fractional topological charge. I mean, a topological charge which is theta over n. So, in some papers, people have in mind a description of the QCD vacuum where the relevant objects are these fractional instantons, sort of instanton quarks as they are called. But in this picture, what you obtain is just a dilute gas of these fractional objects. And so you expect something which is like the instanton gas, but 1 minus cosine of theta over n. Okay, and that will be in agreement with a view in which these objects, these fractional objects, are non-interacting among themselves. But that will lead to a bar B2 here, which is minus 1/12, like in the dilute instanton gas. And this 1/12 is something like 0.08, okay? This is in contrast with what we measure, I mean, which is 0.20 with an error of 2. So we are several standard deviations from this prediction. That means that even if this picture is not completely wrong, but it means that if these fractional objects exist, they are not weakly interacting. I mean, this is what you learn from this result. Now, a few words about the before. Now, before, when we try to fit the value of before from these fits, we get always something which is compatible with 0. That means that we are not able actually to determine this before. And the bound that the present bound is a before which is less than 10 to, sorry, there is an error here. This before is less than 4 times 10 to the minus 4. Now, the only determination that we were able to obtain was for SU2, for 2 colors. And here we got a determination of before after continuum extrapolation with a 30% error, okay, which is this 0.6 with an error of 2 times 10 to the minus 3. Now, if you assume that the before is scaling as 1/n to the 4th, as in the width and ansatz, then you expect before to be of the order of 10 to the minus 4, and this is exactly of the same order of magnitude of the upper bound. Actually, the upper bound is a bit higher than this. It's 4 times 10 to the minus 4. So that means why, I mean, if the large-Nscaling is working, it means that before is expected to be really small for SU3 or larger n. Okay, now what about finite temperature pure gauge theories? Well, the question is the following. We know 2 things, I mean, about finite temperature pure gauge theories. From one hand, we know that there is a critical temperature of the order of 270 MeV, where the theory undergoes a phase transition to the confined phase. Okay, the confined phase where, as you know, there is a spontaneous breaking of center symmetry and the string tension disappears. Now, the other information that we have is that at high enough temperature, we expect that at some point the dilute instanton gas approximation will work, okay, because the theory becomes perturbative, because the temperature puts an effective infrared cutoff on the side of the instanton, so just small instantons survive and they are perturbative. So the question is, how these 2 transitions, I mean, that the second one could not be a real transition, just a transition from 2 regimes. What is the relation between these 2 transitions? I mean, where we have the confinement, where we have a transition to a dilute instanton gas approximation from the large N scaling that we have at 0 temperature. There is any relation between the 2 transitions? Now, there is an answer regarding the topological susceptibility, which was known from, is known from several years, since several years. This is the behavior of topological susceptibility as a function of T over Tc, where Tc is the deconfinement transition, and this is what is a determination of more than 20 years ago. And the result is that the topological susceptibility stays more or less constant at its 0 temperature value until you reach the critical temperature, and then it drops. It drops basically to 0 very fast. So it's not a real phase transition for the topological susceptibility. I mean, it's not an order parameter, but there is a strong decrease as you cross the confinement transition. Well, this result has been confirmed later, and what happens is that as you go to the large N limit, the drop is sharper and sharper. So this is a picture from this paper from 2004. And here on the horizontal axis, you don't have the temperature itself, but the reduced temperature. I mean, the difference between the temperature and the critical temperature divided by the critical temperature, what is usually called in statistical mechanics the reduced temperature. So this vertical axis here signals the location of the confinement transition, and this is the ratio of the susceptibility at finite temperature divided by the topological susceptibility at zero temperature. So you can see again that the ratio is stable to 1, and then it drops, and the drop is sharper and sharper as you increase the value of n. So this is n equals 6, n equals 4. Okay, you can see that for n equals 6, topological susceptibility is almost compatible with 0 after the transition. Okay, so a topological susceptibility which goes to 0 is compatible with a dilute instanton gas approximation regime. I mean, after all, that means that the topological fluctuations are very rare, and so that could mean that you have a sort of description in terms of instantons which are very dilute and non-interacting among themselves. Okay, but this is not completely compelling. I mean, so that this is a strong indication that as you cross the confinement transition, then you switch from a regime where the large-Nscaling proposed by Witten is working to a regime where the dilute instanton gas approximation is working right after the confinement transition. This is not completely compelling, because there are examples that I will show you an example shortly from CPN models, where you may have a vanishing topological susceptibility, but at the same time the dilute instanton gas approximation is not working. So you need to go to higher order terms in the Taylor expansion of the free energy density as a function of theta, and so you need information about these B2 coefficients. I mean, and this is the result that you obtain for the B2 coefficient as a function of the temperature, which was obtained in this paper in 2013. And what you see in this case is that these are results both for n equals 3 and 6. This B2 coefficients, which is compatible with the large-Nscaling that we discussed before, suddenly changes when you cross the confinement transition, and it goes to this value, which is minus 1/12, which is the value predicted for the dilute instanton gas approximation. Basically, it is the value which comes from the Taylor expansion of the cosine. Okay, and you see also in this case that the approach is faster and faster as the number of colors grow. Okay, so this is a confirmation of the fact that as soon as you cross the confinement transition, you switch to a dilute instanton gas approximation regime, which is something which is really non-trivial, because in principle you expect that this approximation works only at asymptotically high temperature. Instead, it works at a temperature which is in the deconfinement phase. And this puts the question of whether there is any relation between confinement, deconfinement, and the topological properties of Yang-Mills theories, so, and theta dependence. And I will discuss more of that later on. Another proof of the approach to dilute instanton gas approximation is by looking at the scaling of the topological susceptibility. This has been done in this paper by the Wuppertal group in 2015, where they look if the topological susceptibility scales like predicted by the dilute instanton gas approximation. This is even more striking because you may have an ensemble of non-interacting instantons But this scaling, which is in agreement with the perturbative prediction, seems to demonstrate that the perturbative prediction is working despite the fact that the temperature is of around 300 MeV, which for sure is not a perturbative scale for QCD. Okay, you are still strongly perturbative, non-perturbative, sorry. So, to conclude this part, I mean, what is the emerging picture for SUN pure Yang-Mills theories? The emerging picture is the following. Shortly after TC, you have the topological excitations behave as a dilute non-interacting gas with the free energy density which behaves as follows. Now, I didn't discuss this, but from this picture, I mean, from the deviations that you see of B2 from the dilute instanton gas approximation, you can also make a deduction. I mean, you can infer that the residual interactions that you have among instantons in this regime, so soon after the phase transition, are repulsive. Okay, and why that? Because you can make a sort of virial expansion of the free energy density, and from the deviations that you observe, you can deduce what is the nature of the interactions. I mean, if they are attractive or repulsive between instantons, and the sign of the deviation tells you that they are repulsive. Now, then the scenario changes completely if you imagine to cool down the temperature. As soon as you cross the confinement temperature and you move into the confined phase, where center symmetry is restored, then what you observe is that the theta dependence suddenly switch to the behavior predicted by large N scaling. Okay. And this already said, I mean, that this switching sometimes is interpreted as a decomposition of instantons into what are called the instanton quarks, so objects which carry a topological charge 1 over n, when n is number of colors, but this is in some sense falsified by the numerical data. I mean, falsified in the sense that if this object really exists, they are not weakly interacting. I mean, you can measure the interactions among them. Maybe, I mean, the value that we obtain could be used in some effective models to model the interaction, I mean, this object. I don't know. I mean, this is just something which could be done in the future. Now, before switching to full QCD, let me point out that in Yang-Mills theories, large N predictions regarding topology are just qualitative. I mean, as you have seen, you can just make enhancements about the scaling of the Taylor expansion coefficients, which are expected to scale like 1 over powers of 1 over n. You cannot make really quantitative predictions because Yang-Mills theories is a matrix model, so even large N expansion cannot make exact computations. But if you go to simpler models, like CPN models in 2 dimension, which are vector-like theories, then in this case you can make quantitative predictions in the framework of the 1 over n expansion. And so just two couple of lines to explain you what are these CPN models. They are in 2 dimensions, they are 2-dimensional models, and the variables are these complex fields which have n components. So it is a complex field which are constrained to have modulus 1. Okay, and even if in this case the gauge field is not a dynamical variable, but you can make a formulation in which the gauge field, U1 gauge field enters the game in terms of this covariant derivative. And so in this case you can add a topological a theta term to the action, and this is a 2-dimensional theory with a U1 gauge field. So the topological charge is the topological charge for a abelian field in 2 dimensions that we have discussed in the previous lectures. Okay, just to tell you what is the topology of what in this case. Okay, it is just the topology of U gauge fields in 2 dimensions. And okay, here there is a list of large N analytic predictions for these models. Now you have the topological susceptibility, which is predicted to scale like 1 over n. So in this case, it vanishes in the large N limit. This, in contrast to what happens for QCD, in this case, the topological susceptibility itself is expected to vanish as 1 over n. And the B2 coefficients are not in agreement. Okay, this is the example that I was mentioning before. This is an example where the topological susceptibility is vanishing, but you don't have a Dilute instant. The Dilute instant gas approximation is not working. Okay, despite the fact that the topological susceptibility is vanishing. So despite the fact that the probability of finding topological charge different from 0 is going to 0 in the large N limit in a given portion of volume. Okay, the B2N coefficients are also predicted to the leading order in 1 over n, predicted to scalars inverse powers of n, and the first few coefficients have been computed analytically. So, for instance, you know that the topological susceptibility times the correlation length squared of the system must be 1 over 2 pi n plus corrections which have been computed. This is the prediction for the first corrections. And at the same time, you have predictions for the leading order behavior in 1 over n of these further coefficients. So in this case, one would like to see if also the quantitative these quantitative predictions are verified by lattice simulations. In some sense, in SUN gauge theories, the only quantitative prediction is for the topological susceptibility, but it is not a theoretical prediction. It is a phenomenological prediction. I mean, you measure the mass of the eta prime, and you and then from that you deduce what is the value of the topological susceptibility. In this case, you can compute it in the theory. Okay, and well, the lattice results are in agreement with expectations. So in these two pictures, there are the results for the topological susceptibility and for B2. In both cases, they are multiplied by n, the first quantity, and by n squared, the second quantity, so that you expect in this case, by this factor in front of them, you expect them to approach a finite value in the large N limit. And this finite value comes out to be in agreement with the prediction, and also the first corrections are in agreement, and we also obtain a prediction for the further coefficients in the 1 over n expansion. Okay, which I don't know, hopefully they will be verified sometime by analytic computations, but I have to say that analytic computations are a nightmare. So I think that going one order more in the 1 over n expansion, I don't know if it's feasible, I mean, from an analytic point of view. But in this case, what you observe for these theories is that the 1 over n convergence in any case is quite slow. I mean, the observation is that the corrections are large. If you look at the scaling of these coefficients, you have 0.05, then the next coefficients for the topological susceptibility is 1.5, which is almost 2 orders of magnitudes larger, and the same happens for B2. So that shows that this 1 over n expansion for these models maybe is not very useful. I mean, it works, but I don't know how it is useful to make predictions for small n, okay, because the convergence is poor. This is not what happens for SUN Yang-Mills theories, and it is usual to say that in SUN n equal to 3 is already large, okay, because what you measure for n equal 3 is already very close to the large n limit. this is not the case for these two-dimensional models, but of course, this is not what is more interesting for us. And for us, it's more interesting to switch to what we can say about full QCD. Okay, but first let me stop for a couple of minutes to see if you have any questions up to now. So, no questions? Okay, then I will go on. So let me go to results regarding full QCD, and let me start from this study, which regards directly QCD with physical quark masses. So this was a study regarding an F equal 2 + 1. So we have two light flavors and a strange quark with physical values of the quark masses. And discretization was a discretization with staggered fermions, in particular such improved staggered fermions and an improved gauge action. And we made use of cooling to determine the topological background of gauge configurations. Now, as you know, as we discussed last week, for QCD with light quark masses, you have quite robust predictions coming from chiral perturbation theory. So this horizontal line here is the prediction from chiral perturbation theory. And in this picture, I reported the determination that we obtained in this paper for the fourth root of the topological susceptibility as a function of a square, of the lattice spacing square. So this 0.01 corresponds to a lattice spacing of 0.1 Fermi, which is already a quite small lattice spacing. I mean, usually it is taken as the region where you expect the lattice spacing that cutoff effects start to be well under control. Okay. Now, what you can see from this picture is that when you try to measure the topological susceptibility, lattice cutoff effects are quite strong. Okay, here you have 5 determinations, and these two bands, I mean the gray band and the blue band, corresponds to two different continuum extrapolations. In this blue extrapolation, we just took into account a square effect, and in the gray band, we took into account up to a to the 4 corrections. Okay, so you can see that I mean at 0.1 Fermi, the value that you obtain for the topological susceptibility is actually somewhere in the middle, still from the chiral perturbation theory expectation and what you obtain in the sequential limit, which is this 180 MeV from the Witt and Veneziano mechanism. So even at this small lattice spacing, cutoff effects are really large. And you really need to extrapolate and make use of very small lattice spacing. I mean, this lattice spacing is of the order of 0.05 Fermi, so 1/20th of a Fermi, which is quite small. Without this point, we would not been able to correctly extrapolate to the continuum limit. And luckily enough, I mean, the continuum extrapolation is well under control because the two different extrapolations give consistent results. And it is also in agreement with the prediction of chiral perturbation theory. But now the question is why there are such large cutoff effects when you go to full QCD. And in order to appreciate how large are these effects compared to what you observe in the pure gauge theory, I would like to show you, I mean, it is not in the slides, but let me go for a while to a paper that I have here, and it is this paper that I mentioned in my picture, my review picture about quench the results. So this is the results obtained from Atenodorou and Mike Tepper by Cooling this year, which was one of the results that I reported. And you can see that here the approach to the continuum limit of the topological certability, the fourth root, is quite smooth. I mean, the extrapolation is practically flat for lattice spacing. Here the lattice spacing is reported in units of a squared times sigma. So it's different scaling, but a sigma to the, I mean, the square root of sigma is of the order of 0.5 Fermi, so it is comparable. In any case, you can see that the approach is quite smooth. And this is the quencher theory. I mean, apart from this point here, which is excluded from the fit, but this is due to the fact that here we have topological freezing, which is an algorithmic problem that I will mention shortly, I mean, after. Okay, so the situation in full QCD is very different. Let me go back to the slides. And you have a significant cutoff effect. So why you have such a slow convergence? Now, let me go back to why you obtain such a small value in full QCD compared to what you obtain the quencher limit. You obtain such small values because when you add the dynamical fermions, you are adding to the functional integral the determinant of the fermion matrix. Okay, and if you the determinant of let me write it in a continuum fashion, this slash plus m. So if m is very light and you have a zero mode of the Dirac operator, so a fluctuation of the topological charge to values which are different from zero, then the determinant is suppressed. Okay, so because you have zero modes in presence of zero topological charge, so because of the Atiyah-Singer theorem, which relates the number of zero modes to the topological charge background, the determinant is suppressed, and that means that non-zero values of Q are strongly suppressed in the path integral, and that is this is the reason of this small value that you obtain with light flavors in chiral perturbation theory. And actually, if you extrapolate to zero quark mass, the value would extrapolate to zero. Actually, this value will go to zero. Now, the point is that this suppression of topological modes takes place if your Dirac operator is a good discretization of the continuum Dirac operator from the point of view of chirality. Okay, because if you don't have well-defined zero modes in the slash operator, then you will not have suppression of topological charge fluctuations. So in this case, we are using staggered fermions, and the staggered operator is not a perfectly chiral operator like also the Wilson one. I mean, you don't have exact zero modes for this operator. Okay, like you have, for instance, with the overlap operator with some operator satisfying the Gisbert-Wilson relation. So that means that the definition of zero modes for finite lattice spacing is approximate, and also the suppression of topological charge fluctuation is approximate. So what is happening here is that the determinant of the fermion matrix is not playing properly its role, and its role is to suppress the topological charge fluctuations. Okay, and as you approach the continuum limit, then it starts working better and better, and you see this suppression, and finally you approach the continuum limit. But you may have continuum corrections which are much worse than in other standard observables. Okay, is that clear? Do you have questions? Okay, fine. So now one problem with the need of approaching such small lattice spacings, you may say, okay, what is the problem? I can go to very, very small lattice spacing and I will recover the current properties. Okay, it is, in general, this is inconvenient because you need the autocorrelation times of the observables are much longer, and you need also bigger lattices, and you have to spend much more effort. But in the case of a topological charge, as you go to very small lattice spacing, there is another problem that you have to face, and this is the freezing of topology. And it is better shown by the following pictures, which refer to the same paper that was in the previous slide. This is how the topological charge fluctuates during our Monte Carlo simulations. In this case, of course, it was a full QCD simulation, so the Monte Carlo algorithm is a hybrid Monte Carlo, more precisely a rational hybrid Monte Carlo, because with staggered fermions we have to take the fourth root of the determinant, so we had to use a different algorithm to simulate it. And this is the Monte Carlo history of the topological charge for 3 different values of the lattice spacing, going from 0.08 Fermi to 0.0 almost 0.06 Fermi, which is basically the last point that we had here. I mean, okay. So this is the point that is shown here as a blue Monte Carlo history. And now the question, why we didn't go to smaller lattice spacing? Because if you go to smaller lattice spacing, essentially the Monte Carlo history of the topological charge is flat. I mean, in the sense that from the point of view of topology, the Monte Carlo is dead. Okay, so as you can see, we kept it on for 3,000 Monte Carlo trajectories, and then we switched off the run because it was producing nothing. I mean, it was useless. And why it is zero? It is not zero because the topological stability is zero in this case, but it is zero because you can see that there is a reduction in the fluctuations, and also there is the scale, the time scale of these fluctuations is longer and longer. What is happening here is that the algorithm is no more able to switch from one topological sector to the other. Okay, this is a very hard algorithmic problem, which is common to basically to all models where you have a non-trivial topology. Okay, and the reason, the underlying reason, is that standard algorithms that you usually use, in some sense, move continuously through the configuration space. I mean, they make small changes, local changes, or even when you make use of a hybrid Monte Carlo, which is a global algorithm. I mean, it changes the configuration as a whole. I mean, it evolves it in a local way. But in any case, what you do is to integrate in equations of motions during the hybrid Monte Carlo. So you are changing your fields continuously. And when you change your fields continuously, when you really approach the continuum limit, where the definition of homotopy classes become effective, then you are not able anymore to switch from one sector to the other. Okay, and this is what you can see here. And this is visible not only in this context, but it is visible in every model. And for instance, in this picture, I show you what happens with the topology, with the particle on a circle. So the first model that we discussed last week. So this the figures on the bottom are from the simulations of the particle on a circle approaching the continuum limit. Now, approaching the continuum limit means that here in this value appearing here, n, which is 1000, 1200, and so on, is the number of temporal slices, okay, for this path integral. So this is n, the number of slices, number of lattice sites that you have in this one-dimensional model. And so these are simulations which are done with the fixed physical temporal sites, so at a fixed temperature, but increasing n. So as n increases, it means that you are approaching the continuum limit. As you can see the same thing that happens in full QCD. I mean, as you approach the continuum limit, the fluctuations of the topological charge as a function of the Monte Carlo step are slower and slower until they get stuck in one topological set. Okay, exactly what happened before. And again, in this case, the reason is that you are updating the configuration by small steps. And when you approach the continuum limit, the small steps that you can do are smaller and smaller. Otherwise, the acceptance is low. And if you do small steps, you will not change for sure the winding number of the path. Okay. Well, this is observed also in, for instance, in SUN pure gauge theories or also in CPN models. Now, and one feature when you have models which depends on some large n, like SUN gauge theories or the CPN models, is that this problem of freezing, and you can look at it from the point of view of the autocorrelation time of the topological charge. And what you can see is that this autocorrelation time grows exponentially with the correlation length of the system, which is proportional to 1 over A, 1 over the lattice spacing. And the fact that it grows exponentially is visible from this picture, which I took from this paper from 2004 from Luigi Ettore and this student, Manca. And you can see that in here it is a bilogarithmic scale. I mean, both the horizontal axis and the vertical axis is logarithmic. So usually the behavior that you have for standard observables is that as you approach the continuum limit, the autocorrelation time grows as a power law in the correlation length. Okay, but you can see that a power law in a bilogarithmic scale means a straight line, and you can see here that it is not a straight line. I mean, it keeps growing. Also the slope of these lines. It means that it is exponential actually in the correlation length, which is a kind of critical slowing down, which is much worse than what you observe in standard observables. And it is typical of topological observables, and it is related to this fact that the freezing itself is related to the homotopy classes. I mean, you get stuck in one homotopy class, and unless you invent a very smart algorithm which is capable of jumping from one sector to the other by itself, because it is a magic algorithm, unless you can do that, you are stuck. Okay. And another feature is that this critical slowing down seems to get worse and worse as you increase the value of n. I mean, this is what you observe both in SUN gauge theories and in these CPN models. I mean, this is also visible in this second picture, where you see that the behavior of the autocorrelation time as a function of the correlation length can be given in terms of this scaling variable, which is approximately psi times n. Now, from a qualitative point of view, why the situation gets worse as n increases, there are many possible heuristic explanations of this. One possibility is that, as the n increases, the typical configuration with a non-zero topological charge are larger and larger. The size distribution of instantons get concentrated around large instantons, and it is more and more difficult to decorrelate the presence of large instantons. You get frozen more rapidly. Okay, but this is quite heuristic. So this is one problem that we will discuss more in detail next week. I will discuss some algorithm which can alleviate this problem of topological freezing, which is one of the main problems in studying topology. Okay, but let me go back to the results for full QCD, unless you have some questions regarding this. So let me stop for a few seconds to see if you have any questions.
Maybe I have one question.
Yeah, sure.
So what you're saying is, if we are at a given lattice spacing, let's say A equals 1 or something, a big lattice spacing, a given size of the lattice, then in that setting, it is easier to jump to another value of the action, which will be separate.
Of all the topological charge.
Yes. Yes. Even if, like, our Monte Carlo will take, let's say it will update locally, but since the value of the lattice spacing or is larger and n, the lattice size is smaller, we can jump to another sector. But
yeah.
Okay, and if we keep decreasing A, then where we will make the local jump is something very close to what we were before, and hence we will not be able to move out of the well, let's say one topological sector well. That's what
Yes, exactly. Yes, it works exactly in this way. Maybe we can discuss this point going to the previous picture. When you consider the particle on a circle, this is for instance, a discretization of the path for a given value of n. Now, what happens when you decrease the lattice spacing? More or less, let me say it in this way. If this is the lattice spacing, so let me call it A, then if you look, for instance, in particular at the path integral distribution of the paths in this case, the typical distance that you have from one side to the other, in one step, from one point of the path to the other, as you approach the continuum limit, it goes like the square root of A. Okay, so it means that as you go to A equals 0, to the continuum limit, the typical distance from one side to the other will be of the square root of A. It means that if you try to make a larger jump, which would permit you to have a different winding number, then most of the times it will be rejected if you adopt a Metropolis algorithm. Okay, just because in the continuum limit the path tends to be continuum. Okay, so if you try to make a big jump, a big local jump, then most of the time it will be rejected. Okay, and this is how the homotopy is enforced in some sense. But it is enforced not just only in the path integral, but in this case it is enforced also in the algorithm, which becomes unergodic.
Okay.
So in some sense, you should invent a different algorithm which permits you to make directly a jump, while having a large acceptance. Okay, actually, for the particle on a circle, this is possible. I mean, you can invent a magic algorithm which does exactly this. I mean, that is able to jump. I mean, what I mean is that if I go back to this fake picture that I had yesterday, I mean, of the topological sector, which I draw like this. I mean, the point is that can I make a jump from here to here? I mean, from two configurations which are more or less the same action. So the jump is accepted from the metropolis, but I jump from one sector to the other. Well, you have to be very smart to invent this algorithm. I mean, in this case, you don't have to be very smart because it is quite simple. But if you want to do this for a complex theory like SUN, then you have to be very, very smart. And of course, this algorithm does not exist yet. I mean, so, but this is the point. I mean, yes. I hope, I mean, it was clear now.
Yes, yes, okay, thank you.
Okay.
Can I ask something? But why do you always have Q at 0 here? If you enforce at a small lattice spacing some other value of Q, it stays.
Of course, yes, yeah. Sorry, I started.
Right?
Yeah, I started with Q equals 0.
Okay. And then I have another question, but I'm not sure. I mean, maybe it's long. I mean, or you want to talk about it later. So if one doesn't have periodic boundary conditions but open boundary conditions in time, I've heard claims like topology can flow in and out of the lattice, and I've never really understood what that means, but I'm not sure if it's complicated and long.
No, okay, I will discuss it in the next lecture. I mean,
okay.
I will make a list of proposals to avoid this problem, and open boundary conditions is, of course, one possibility. Okay. Then you have the problem that you end up with open boundary conditions. I mean, if you like to have periodic boundary conditions to have an integer value topological charge, this may be a problem if you have open boundary conditions. But there is a compromise that I will discuss next week, which is an algorithm proposed by Martin Assenbusch, where you can open and close the window. Let me say this way. I mean, you make a sort of parallel tempering where you have periodic boundary conditions, but then you let the system to open the boundary conditions and then reclose them, and it works. Okay, I will show you next week. Okay, so let me go back to FullQCD again, and so about finite temperature results now. So I showed you this result that I showed you in this slide were about FullQCD at 0 temperature, I mean, where we expect chiral perturbation theory to work. Now let me go to finite temperature. The original purpose of this paper was about finite temperature, and it was because of axion phenomenology. Now, these are the results that we obtained for the ratio of the topological susceptibility at non-zero temperature divided by the topological susceptibility at 0 temperature as a function of T over Tc. So we observed basically, as in the pure gauge theory, we observed the topological susceptibility almost compatible, a ratio almost compatible with 1. So it means that the topological susceptibility stays almost unchanged from 0 temperature to the pseudo-critical transition in this case. I mean, it's not a real transition in FullQCD, but it's just a pseudo-critical transition. And then it drops. I mean, this is a logarithmic scale, so it drops exponentially. I mean, as a power law, sorry, in the temperature. Okay, this is logarithmic in both axes. So a linear behavior means a power law behavior, decreasing power law behavior as a function of the temperature. But then we obtained a a result in contradiction with the dilute-Thiessen gas approximation. In the prediction from the Daiga approximation was for a coefficient around between 7 and 8, okay, depending on the fermion mass. Of course, this dependence going from 7.6 to 8, it depends on the value of the fermion mass. But what we observed was a coefficient 2.9, so more than a factor 2 smaller than what predicted by the dilute-Thiessen gas approximation. And it was a striking result. And it was a striking result, and despite the large cutoff effects that we observed at zero temperature, and the game that we played was to divide everything but the value observed at zero temperature at the corresponding lattice spacing, and indeed we had the fake impression that it was working, because after this rescaling, all the data at different lattice spacing seem to be over each other. Okay, and so why this result is important? I mean, this why this is important to axion phenomenology. Now, I don't have the time to explain everything in detail, but basically, how the topological susceptibility changes with temperature is important for axion phenomenology. Now, let me make a picture which maybe tells more than what is written in this slide. And if you remember, this axion is the Goldstone boson of some spontaneously broken symmetry, which is this Peccei-Quinn symmetry. And now, then you have the coupling to the theta term, to the QCD theta term, to the GG dual of this axion, and that breaks the symmetry explicitly. And it is like making a tilt of this Mexican hat. Okay, so like moving it in this way, and so you have a minimum. Okay, instead of having a flat Mexican hat, you have a minimum here, which is the point where the effective theta term is 0, and the curvature is gives you the axion mass, and at the same time it is the topological susceptibility, because it is the theta squared term in the theta dependence of QCD. Now, when you have this Peccei-Quinn symmetry breaking, the axion field can be anywhere. Okay, so at some point, I mean, the model is that at some point during universe evolution, you had this spontaneous symmetry breaking, and the axion field could have been anywhere here. Okay. Now, what happens? What happens is that normally you would expect that the axion field, since it is not, you have this misalignment. I mean, the axion field initially is not aligned to the real minimum of the effective potential. Then it will start to oscillate around the minimum. Okay, and this oscillation, from the point of view of field theory, corresponds to the number of axions that you have. Okay, so to the energy of the so you can actually, in this misalignment mechanism, you can infer the number of axion particles, the density of axion particles that you have in the universe from the amplitude of these oscillations. Okay. Now, at extremely high temperature, the topological susceptibility is very small. So what does it mean? That that basically at asymptotically large temperatures, since the topological susceptibility goes to 0, then the Mexican hat is still flat. So basically at 0 topological susceptibility, there is no oscillation at all, because the effective potential is flat still. Okay. Now, at some point, the topological susceptibility starts to be non-zero, so this tilt starts. So this part of the potential starts moving, and it moves proportionally in some sense to topological acceptability. And so the axion field, the misaligned axion field will start to oscillate. But then if you write down the field equations in some approximation, you have to take into account also the expansion of the universe. So you have to take into account the Hubble constant and the final equations that you end up with in an approximation of, you just take the zero mode approximation for the axion field. I mean, you treat it as a field which is uniform over all space. You end up with an equation which is something like a damped harmonic oscillator, okay, where the damping comes from the Hubble constant and the oscillating term comes from the axion mass, but the axion mass is related to the topological acceptability. So we have a crossing point between the Hubble constant and the topological acceptability where actually the field starts oscillating. I mean, until the tilt is not large enough, because of this damping, the axion field stays stuck on this value, and you have to increase the tilt or decrease the damping as the universe expands until the field starts oscillating. And at that point, if you work out the equations, at that point, the number of axions that you have in the universe is fixed. Okay, and so you can infer from that the number of axions that we have today, and if you make a strong assumption, but you are playing with assumptions in this game, you make a strong assumption that the amount of axions corresponds to the amount of dark matter that you observe in the universe. In this way, you are able to fix finally this constant, which is the unknown constant in the axion model. And finally, you are able to fix what is the value of the axion mass that you should observe today. And you can finally tell to your experimentalist friend, okay, you should observe an axion mass which has this value. So set up your experiment so that you can measure this mass. Okay, so this is, in a few words, the whole game, why this determination of the topological acceptability is important for axion phenomenology, because it permits you to fix this point where the axion field starts to oscillate, and that fixes the number of axions, and that fixes this coupling constant f of a, and then that finally fixes the value of the axion mass today, which again is fixed by the fact that you know that topological acceptability today is the one predicted by chiral perturbation theory. So using our data, we predicted a value of the axion mass which was 10 microelectron volt. Okay. Now, in a later lattice study from different groups, but in particular from the Wuppertal Budapest group, they obtained quite different results. I mean, they obtained a topological susceptibility decreasing as a power law in agreement with the prediction of the dilute Instanton gas approximation, and that changes, not dramatically, but it changes the value of the axion mass by 1 order of magnitude, more or less. It goes to 100 microelectron volt. And the change is not dramatic because the axion is searched in a range which covers several order of magnitudes, but it can be dramatic for many of these windows are already closed by experimental observation, so a few windows remain, and it is important for present experiments trying to detect axions to know what is exactly the scale. I mean, this can leave some experiments out of the game. Okay, and let me discuss, I mean, what was the main strategy leading the Wuppertal group to obtain these quite precise results that, as you can see, goes up to 2 GeV in terms of temperature. Now, these improved results were basically based on 2 main strategies or assumptions. So the first problem, again, I mean, they showed clearly that we still, in our data that I showed you before, we still have, despite this fake scaling to the continuum, we still had some strong lattice artifacts, which are still related to the bad properties of the determinant, of the fermion determinant. And so they show that clearly in this picture, where you can see, I mean, we had this, these red points are our points, actually. And so you can see that they repeated our simulations, and they saw that in this region, the ratio was flat. This ratio, I mean, this, on the horizontal axis, you have 1 over nt squared times some factor, and nt sets the value of A just because the temperature is 1 over nt times A. So at fixed value of the temperature, basically, as you increase the number of lattice spacing in a temporal direction, you are decreasing the value of the lattice spacing. So usually, finite temperature continuum extrapolations are reported as a function of 1 over nt squared. So basically, the points that we had were these 2 points here that seemed to be flat, but then I mean, they went to lattice spacing beyond, and what they saw is that there is a start to a decrease, also from a different determination without taking this ratio. And what is the strategy that they adopted in order to account for these bad properties of the fermion determinant? Okay, the strategy was the following. I mean, the problem is that when you consider again the determinant of this slash, we should suppress the topological fluctuations. So basically, if you have a zero mode, then you expect to have an eigenvalue which is MF. Okay, because you have just the mass of the fermion, and that is the suppression of the topological fluctuations. I mean, the topological fluctuations are suppressed as powers of the fermion mass. Okay. Now, if you don't have an exact zero mode, so you have instead of a zero mode, you have some lambda because of the bad chiral properties of the Dirac operator. Then instead of having MF, you have this MF plus this I lambda. Okay, the I comes because the slash is anti-Hermitian, so the eigenvalues are purely imaginary. Okay, so what they did is to reweight the configurations. I mean, they measured, they produced the Monte Carlo sample of configurations. They measured the eigenvalues of the staggered operator. They measured the topological charge background by standard cooling or Wilson flow. And they said, okay, if I have a zero topological charge, then I would expect to have an eigenvalue which is MF. Instead, I observe MF plus I lambda. And then why don't reweight the configurations by this factor? Okay, so that the determinant was not smart enough to make the suppression, and I will help it to make it afterwards. So post-processing the configurations. Okay, and these are these results that you can see here. I mean, these reweighted results, which are reweighted in this way. Okay, and it works very effectively. I mean, you can see that the lattice, the dependence on the lattice cutoff is almost suppressed. I mean, you obtain a flat result and a very smooth extrapolation to the continuum limit. Now, of course, it is a post-processing of the gauge configuration. So it's not something that you are doing directly in the Monte Carlo simulations at the level of defining your theory. It's something that you are doing afterwards. And the question is, what is the effective modification that you have on what you are studying? I mean, this afterwards reweighting can induce some non-local modifications in the simulated theory. And you don't know, in principle, what are the other possible effects, but it seems to work very effectively. And then, and this is the last slide for today, there is another problem that I didn't mention yet, but it is time to mention. Of course, you have the freezing problem. Okay, you have even with a finite temperature, you may have freezing so that you get stuck in one topological sector. But you have another problem. Even if you don't have freezing, you have the problem that you have to sample very rare events. Now, let me make an exercise with you to understand what is this problem of rare events. Let's take this this picture where from the Wuppertal group, where you have the topological settability in units of Fermi to the -4, and you can see here that the vertical axis is in logarithmic scale, and it is in powers of 10. Okay, so let me take the value of at 1 GeV, temperature equal to 1 GeV. Okay, here the topological settability is 10 to the -8 in these units. What does that mean? It means that suppose you can produce at this value of the temperature a lattice for volume which is 10 Fermi to the 4th. It is a huge lattice. I mean, it is. I don't think there are simulations or very few simulations in the market which can afford a lattice as big as 10 Fermi, okay, for each site. But suppose you can do that. That means that if you compute what is the expectation value of Q square, which is topological settability times the Ford volume, here, if you suppose that V4 is 10 to the 4 Fermi, then you obtain 10 to the -4. Okay, what does that mean? It means that even if your configurations are completely decorrelated one from each other, you expect to have Q different from 0 every 10 to the 4 configurations, more or less. Okay, so your Monte Carlo history of Q will be flat, basically flat. Okay, it will stay at 0, and sometimes you'll observe a spike corresponding to 1 or -1. Okay, and that means that I mean, if you have to compute this Q square numerically, you need a Monte Carlo time history that even if the configurations are decorrelated from each other, you need a Monte Carlo history which can be much longer than this 10 to the 4 in order to properly obtain a reliable and usable statistical errors on Q square. Okay, this is what I meant by the problem of computing rare events. And I will show you also next time how can you deal with this problem effectively. But now the approach from the Wuppertal group was the following. They say, okay, since we know that just Q equals 0 and Q equals 1 are the important sector, what they do is not just to sample Q, but they determine the temperature dependence of this ratio, of the ratio between Z1 and Z0. I mean, you can see at this as determining P of topological charge 1 divided by the probability of topological charge 0. I mean, this you don't need to sample this. I mean, you can obtain a determination of this ratio by measuring a smart measuring of the pure gauge action. And this is what they do, and this is how they can obtain a determination of chi up to very high values of temperature, where the topological susceptibility is strongly suppressed. Okay, but one problem also in this case is that in some sense you are assuming a priori that the information contained in topological sector 0 and 1 is the only information that you need. I mean that the other topological sectors are not relevant. Now, this is true if the volume is small enough, but as you take the infinite volume limit, you know that this is not the case. And so you may have deviations from the diluting gas approximation which are not visible on a small volume and with this a priori approximation. So one point is that it will be important to have independent checks of these findings, which I should really do, and I will show you some steps in this direction in the next lecture. But one point that should be clear is that there are three monsters to be defeated. In order to do that, you have to defeat topological freezing. Then you have to be able to perform a correct sampling of these rare topological modes that you have at very high temperature. And finally, which maybe is the most important effect, you have to deal with these discretization effects that we have in QCD with physical quark masses, maybe trying not to do an afterwards reweighting, but just trying to make your Dirac operator behave in a better way. Okay. And okay, I will discuss more on this in the next lecture, and let me stop here. And I think that I finished the slides also in this case, so it's a good point to stop. Do you have any questions?
So just a confirmation, basically, but basically we could have some better, like a better scaling properties at and reach some good chiral properties of the topological susceptibilities. For example, avoiding just in principle, I mean, avoiding the discretization of the staggered fermions and switching to something like, I don't know, a domain wall fermion, and in that case we shouldn't find this slow approach, this slow scaling. But I guess that then we pay it with the fact that they are far more heavy from a numerical point of view.
Yes, exactly. I mean, you can play that game. Of course, if you use a better Dirac operator, then it will work much better, but you have to spend more effort.
Exactly.
At the end, you have to say what is the payoff. I mean, if you have to spend more effort, but you obtain the correct result at a larger value of the lattice spacing, maybe at the end it will be convenient. And another interesting result that I will show you next time is that there are results in the literature which seems to show that if you change the definition of topological charge, so for instance, if you adopt a definition of topological susceptibility which is based on the spectral projectors, then the situation seems to improve. So the lattice artifacts seems to be much suppressed, and this is not well understood. I mean, I have a naive picture of why it works, which maybe I will discuss next time, which is that if you adopt, I mean, in some sense, if you adopt a bad fermion matrix in the path integral measure, okay, that it is missing to suppress some topological modes, and then you adopt the same fermion matrix to measure the topological charge, then they are bad as well, and they will not see the topological charge properly, and finally everything will scale well. Okay, I think it is very naive, I don't know, but I will show you next time the results from the obtained in QCD with the bispectral projectors, which seems to show a much better scaling compared to a gluonic definition. Just when you use dynamical fermions, of course. When you use in pure gauge simulations, they behave exactly in the same way.
Yeah, sure. And just a curiosity, like to check if this game is worth it, is there some group working on topology with some domain Wolf fermion, something like that? Because both the Wuppertal and Pisa group works on staggered.
No, yes, of course, there are groups working with domain Wolf fermions or with overlap fermions.
On topology, I mean.
Maybe also on topology. I mean, I don't know if they are working with physical quark masses. I mean,
okay.
Which is the other point. I mean, these simulations are made with physical quark masses, which are the one relevant for axion phenomenology, of course.
Sure.
Yeah.
Okay, thank you.
Well.